Hello, everybody. Thanks for joining us. I think we can already start. It's 4 o'clock in Grenoble. So we welcome all you today at tinyML Meetup Talk. The main objective of this event is to support the ultra-low power machine learning community and to expand the tinyML ecosystem. My name is Irina. I'm the organizer of today's tinyML meetup discussion. Traditionally, at the beginning of the event, I would like to say a couple words about the sponsors who made this initiative possible. Strategic partners of tinyML Talks: Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, PhotoHub, Greenwaves Technologies, Groovity Incorporated, HOTG, Imagimob, Itemis, ClickAttack, Latent AI, Maxim Integrated, Analog Devices, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Rixen, SAP, Seed, SenseML, Sony Semiconductor Solutions Corporation, ST, Stream Analyze, SynSense, Sentient. There were a couple events that just took place in the tinyML community. Presentations are available, and please use this link to check all the presentation videos and discussions. tinyML Research Symposium just finished, and please go ahead and check this link. I would like to mention 2 words about the community, which is already almost 9,000 members. Please click on the link and sign up for the group. On the LinkedIn, it's also very lively discussions. Please join us there. And of course, check out the YouTube videos. There are more than 360 videos, 6,000 subscribers, so please go and check all the videos, and of course after each talk all the videos will be uploaded on YouTube. So just to mention the next talk that is going to be tomorrow, please sign up. Novel device and materials in emerging memory for neuromorphic computing. For those who is interested, please go and check. I'm going to present introduce the moderator today is Martin Krum, VP of Marketing Greenwaves. Hello, Martin, and thanks for helping me. Martin, please.
Hi, Irina.
Introduce our guests.
Hi, so today we're going to have Łukasz and David from Contact.io, who are going to discuss a product that they've created called PortalBeam. Łukasz has a strong background in embedded engineering, worked on public safety systems at Motorola, and is now looking after R&D for hardware at Contact.io. And David has a PhD in physics, again, full stack embedded engineer, and really is the person behind the software logic in PortalBeam. So I'll pass it over to Łukasz. Take it away.
So let me just introduce myself once again. I'm the CTO at Contact.io. I'm leading basically all the technical related activities, R&D, and I had the pleasure to lead the PortalBeam project as well. And I would like to share today a little about this project and how much it changed the way we are working, our portfolio, and I guess you will enjoy it a lot. First of all, I would like to just give you a little background of Contact.io. The company has been established right now. It's roughly 9 years ago. It's a company with the Polish DNA. The headquarters is in Krakow, but we also have offices around the world, in New York, Berlin, and San Francisco, so in the heart of the Silicon Valley. We started as a company who was positioned as a bigger manufacturer. Right now, we almost finished the transition to be more like the solution provider type like company. Right now, we have more than 1,200 partners around the world from a variety of the industries, from manufacturing, healthcare, transportation, governments. Our products are on the San Francisco airport and many different places. Currently, we manage roughly 2.5 million of connected devices through our cloud. By manage, I mean we are constantly receiving and processing data from them. So basically, these are the live devices. I can't really tell you how many of those devices are already dead, but it's a really big number. And those devices are from very small beacons like that one to the very big and sophisticated stuff like the PortalBeam we'll be talking about today. So going to the point, a few words about the PortalBeam, about the genesis of the product. Because we started to work with the healthcare companies and not just healthcare, but also some kind of public spaces. There is a constant need of monitoring presence of the people inside the different rooms. If we are talking about the offices, this is all about the cost savings. Yes, if we have the conference rooms, we would like to know how much are they utilized, because maybe we don't need 1,000 of them, we just need 400 of them. So the PortalBeam is kind of answer and is trying to solve the problem of monitoring occupancy inside the rooms. A very similar situation in a healthcare industry. We also would like to know how many people are in the room, let's say in the patient room, what is actually happening in there. That's one of the problem we are solving. The other one is trying to get some insights on how people are moving inside the buildings. How many people are inside, how many people are outside, how are they moving across the different spaces, even not individual rooms. That's why the PortalBeam can also work in the mode, so it counts the people moving under the device. That's I would say another stuff. Of course, if we have a device which is working inside the rooms, so maybe we can do some kind of environmental sensing, and of course we can. We also have some environmental sensors like temperature, like humidity. We can also measure air quality inside the room. Everything, something like all-in-one device. And the huge advantage of it is that from the very beginning, we put a lot of effort and focus on very friendly installation and easy installation. That's why our product can operate purely on batteries for up to 4 years, still doing occupancy, let's say every minute, which I believe is something really amazing, especially if we are talking about the device which is doing all the, let's say, AI stuff on it. Yes, so there is no cloud processing. Everything is, we can say, on the edge. So no data transferred, which from the privacy point of view, it's really, really important. To give you some overview, this is the device. So now you can have some kind of a perspective. How big is it? It's really tiny stuff and really, really easy to install without any special training. Okay. Some tech spec, tech specification. So the main connectivity interface is Bluetooth Low Energy. Yes, so everything we are sending out of the device or we are sending into the device is done over BLE connection. So as you can imagine, it's not anything close to the Wi-Fi, no wideband. So we are very limited in the amount of data we can send. So that's also the reason why we're doing all the processing inside the devices, because sending pictures it's no go. Yes, there is not enough. But the another functionality inside this device, which is supporting our room occupancy, is the IR, which means infrared data protocol. So the PortalBeam can easily communicate with our other devices, like for instance this badge, using the IR, and as a result, we are getting something we call the room level location certainty. So because the IR as a light is not penetrating the wall, we can position individual people within the room. Of course, environmental sensors. This is something I mentioned before. Battery operated. It can be also powered from the external power source, which is actually necessary for a footfall mode of operation. I will be talking a bit later. One of the main concerns during the design of the device was, of course, the privacy. And there were a lot of people concerned about the fact that we have a camera. In general, it's not an issue if we're talking about, for instance, office or some kind of a public space. But it's a very much a concern if we are talking about the patient room. Yes, so people are really much confused about the fact that somebody is watching them. So that's why we made a decision that, okay, first of all, we can't use like the regular visual cameras for many reasons, but one of them was the privacy. Probably nobody will allow us to work in a very specific environment. And the other factor is that this camera is very, very low resolution. I think it's fair to say that it's 80 by 80 pixels, which makes any kind of individual people recognition not possible. Yes, so we know that we can see the person, but who's this is almost not possible. I will show this later on. Of course, everything was possible because at some point we decided that we will go with our friends from GreenWave technology, and we started to use the GAPA8 CPU, which is the heart of this the system, and is handling all the let's say AI computations in a very, very power efficient way. Yes, so again, there are a lot of people, our customers, who hardly believe that it's possible to operate on the batteries for 4 years, still being able to deliver that type of a technology. Yeah, that's all about the device itself. Now I would like to focus a bit on the challenges we were facing during the let's say R&D phase. And to some extent, we are facing those problems now, still improving the product, because, you know, the AI development is kind of a process. It's not like something we are delivering and we enter, we learn. We are training our models continuously, so they are getting better and better. And the first issue, maybe not issue, the first challenge we have is because, you know, we would like to cover as much space as possible with the single device. It seems obvious, yes, but this actually have some kind of a positive and negative effects. Like it's very good because I mean the camera we are using, the field of view of the camera is something around 120 degrees. So it's a wide angle camera, definitely. But if we combine this with a very limited resolution, to remind, it's 80 by 80 pixels, it means that in the center of the image, the number of details is really good, but on the edge of the image, like the resolution of the camera is really small. In the picture on the right side, you can see the person who is let's say on the top of the picture is visible with a lot of details, but the person on the bottom left, it's I mean, it's very difficult to recognize, even for us, for humans, that it's a person or something else. Yeah, so that's also the problem where you are attributing the images, yes, because to train the algorithm, you first need to attribute all those people, mark the areas where people are visible. And sometimes it's really difficult. And the other problem is, of course, that because this is the wide-angle camera, the fisheye effect is very strong, and it's sometimes very difficult to map coordinates between the different devices observing the same area or kind of overlapping. Yeah, the next problem on the next, I actually talk a bit about this, is this low resolution. Of course, because of the low resolution, the amount of the computation power we need is of course much lower than if we are talking about VGA camera, for instance. Yes, it's many times less work needed to compute stuff, which of course allows us to process data fast and consume limited amount of energy. That was the main goal of the product. Yes, we need to be operating on batteries. Of course, the privacy is also a factor, but of course, the important is to have a robust algorithm. This privacy was important, but wasn't the key driver. Let me show you a video which actually, yeah, it shows the process how we were collecting the data. It was not possible to collect the data just using the thermal camera because, as we can see on the left side, the level of details was really small. So a person who was doing the attribution, in I would say 70 to 80% of the cases, was even not sure if some object on the picture is a camera, or it's a person, or it's a laptop, or it's a cup of coffee, things like this. And yeah, we realized that yeah, it's no go. Yeah, we have to do the simultaneous recording and get the data from different cameras, because otherwise we'll not be able to record everything in a proper way. As you can see on the left side, there are a lot of hot spots, which at of course the beginning of the project made a lot of confusion to our algorithm. Yeah, the video is quite long, but I think we may go further. Okay. Okay, because I probably switched too much. No, okay, my bad. Bad pixels. Bad pixels is another problem. Because first of all, we have very low resolution, so every single pixel is very important. Here you can see actually a lot of them. Yeah, there are a couple of approaches. As we can eliminate them, we can make the algorithm not sensitive to the bad pixels. But the main problem we started to experience at some point was that it's not like, bad pixels can be dynamic. I mean, if we at the very beginning of the device lifetime have 2 bad pixels, It doesn't mean that when we are scrapping the device, it will still have 2 bad pixels. It can have more, can have less. We spend actually a lot of time trying to figure out the nature of those bad pixels and trying to compensate them. First, because of the algorithm accuracy, but they were also impacting a lot how we are calibrating the images and actually each camera, because this technology unfortunately requires us to calibrate every single camera before we actually ship the product to the customer. And another challenge is the noise. The noise, again, is kind of a nature of those cameras. And at the very beginning, we were suffering a lot from the noise because it caused a lot of false positives. False positives because of the low resolution. If you had a high density noise in some areas, it was misclassified. And you can see the comparison between the image on the left side and right side. It's the picture on the right hand side is after a very basic bad pixel removal, and of course it's denoised. So yeah, I think that the difference is very easy to be seen. Okay, next one. Temperature compensation. That's one of the I think more difficult thing we had to solve. Again, the technology of the camera, we still need to realize that it's of course not the very let's say expensive and high-tech camera, so it is very not fragile, it's very sensitive to the ambient temperature changes. Because the individual pixels have a slightly different, I don't know how to say this, the sensitivity of different pixels varies depending on the temperature. Yes, so the camera is giving a slightly different picture in, let's say, 20 degrees, and a slightly different picture in 30 degrees Celsius. Yeah, there was a lot of effort put into the design of an algorithm which is trying to unify the image no matter what is the ambient temperature. And in the picture below you can see very interesting kind of an artifact, those orange ring around the picture. It's actually the camera enclosure which is still emitting enough heat, and because it's usually attached to the ceiling, the temperature on the ceiling is sometimes 2-3 Celsius degrees higher than on the, let's say, floor level. You can see how much work has been done and how much those two pictures are different. Yes, the one is without any denoising and processing, and the second one is the result. They are not, of course, not the same pictures, but I made them on purpose, selected them on purpose to show you how important is proper, in this case, temperature compensation to get the data which can be fit into the network. Yeah, another problem. We are working with thermal camera. So it's sensitive to heat, and it's sensitive to any source of the heat, but also not the heat, but actually to the cold. Yes, so the big problem for us is sunlight. In the top picture, you can see actually how the sunlight coming through the doors is heating up the floor and other object in the room, and you can see the person within the picture. Yes? So if we calibrate everything, the person seems to be actually a cold object, which is very difficult to be spotted by the algorithm. This is one of the case. Yes, this is something we are experiencing during the let's say summer. But in the video below, you can see what is happening when there is a winter, and the person is coming from outside inside the room. It's definitely not a hot person. It's black. Yes, so this is also something we need to take into the consideration while training the algorithm. And those two pictures, picture and a video, were taken at exactly the same place. So you can see how much they are different. Okay. Modes of operation of the device. Actually, there are two main modes. The first one is the people counting. In a people counting mode, we are making one picture per minute. This picture is then analyzed by the algorithm, and the number of possible people detected is being transmitted over the BLE together with the coordinates of those bounding boxes. This data is then being processed by the cloud. So this opens up the possibility of using multiple beams within the single room, which we call kind of a stitching algorithm. So even if we can't cover the whole room with one device, we still have a possibility to chain them and then eliminate possible duplicates in the coordinates of a single device. In the picture below, you can see the PLE frame output. So as I said before, we are reporting occupancy, so the number of people we detected, and there is a list of the coordinates. Coordinates are camera based, so a cloud needs to do some additional computation to be able to map those coordinates into the floor coordinates. Yeah, the second mode is the footfall. In this mode, we have to be connected to the external power because picture acquisition frequency must be much higher. We can't take a picture every minute because, of course, during that time, the many people will pass away. Here with this, we are taking, I believe, roughly 5 frames per second. So this also gives us the capability of the device, its performance, that we are still able to do all the math, all the AI stuff 5 times per second. But of course, the power consumption is then much higher, and we will drain batteries in 1 month instead of 4 years. And of course, here we are counting how many people walk into the room or walk out of the room. This information is then being sent to the cloud, and cloud, considering the all information from a different sensors, different beams, is trying to put everything together. So we have let's say the total number of people within the area we are monitoring. Yes, this actually I already described, that footfall is powered by the external power source. Occupancy is working on the batteries. To save some energy, we also decrease the frequency during, let's say, night hours, especially in the office space. When we know that there are nobody in the office, we are not making pictures 1 time per minute because it simply doesn't make sense. Yes, so sometimes we can even make the device to work much longer than initially was designed. Very brief description of the processing pipeline. Of course, the first stage is thermal image acquisition. Then we are doing a lot of stuff to compensate the camera temperature, the sensing element temperature. Then it's denoising, some kind of temperature range estimation and normalization, and one of the last steps, there is a whole neural network processing with all the object detection. And then at the end, we are trying to eliminate the detections which we believe are kind of a false positives. So we are trying to sort them based on the probability. And it's an individual device parameter we can configure. So some of the devices can be more sensitive, some of them can be less sensitive, depending on the environment, depending on the amount of different objects within the room, like, I don't know, computers, for instance, which are generating heat, like the air conditioning system. So in those cases, we are increasing a bit the requirement on the probability level. And I think this is more or less everything. And I think we are ready for a Q&A session.
Great. So we had a lot of questions being asked and answered by Dawid, but there's still some questions coming up here. I've got one from Bennett, which is about BLE connectivity, which is really asking about the architecture of the BLE network. Is it a mesh network? How is it connected? You know, how is the device connected in the room?
Okay, so definitely it's not a mesh connection. I mean, for many reasons, we are not the big fans of the mesh, which doesn't mean that it's a let's say the great technology. Usually we are operating in let's say the architecture when we have the BLE end devices like the PortalBeam, sensors, badges, and we have the BLE to Wi-Fi gateways. And those gateways can be ours, but we also are cooperating with different gateways manufacturers, with network providers. So the third-party devices also understands our protocols and can stream data to our cloud. There is a lot of effort put into making all this communication secure and robust. So yeah, luckily so far we haven't had any, let's say, security issues, but yeah, the problem is that sometimes the amount of data we are generating is really big, and we need to have let's say one gateway per, I would say, 50 devices, and so the density of the gateway sometimes is really big.
Great, I was on mute. Yeah, there's another question which is an interesting one. So what type of, well, the first portion of this question is what type of image denoising algo is employed, but I think you did touch on that. But the second portion is, why didn't you add the noise and generate noisy images as part of the augmentation process to the neural network when you were training?
Okay, so yeah, let me answer the second question first. Of course we did. But it looks like sometimes the noise of the camera itself is so big that yeah, it was no other way than try to denoise. I mean, the noise itself is just the one point, but also this kind of characteristic of the camera that it varies depending on the temperature. It was the main problem, yes, because noise itself can be, of course, the problem of the noise can be solved by attribution of the images, but by also feeding the noise images into the training process. But we found that definitely more robust and the denoising made the algorithm much more accurate.
Did you find that it was per camera? Because that's something that I think that we've seen, is that there is some difference between each camera. So augmentation is not going to get you out of that problem.
Yes. Yes, and we can even tell that the problem of the noise can be different between different batches of the cameras, production batches. Yes, so it was a situation that we trained the algorithm using the cameras from one batch, and it wasn't working that well with the cameras from different batch. It was very, very sensitive. So this is also something which is adding a kind of a complication to the whole process.
Okay. There's a couple of questions which are basically just like reconfirming things. So, I mean, basically you mentioned difficulty with low resolution. Did you stick to 8080, which I think the answer is yes. But then another one which said you said it was not okay to use a video camera, but did you actually use a video camera? And I think the answer is no. So, am I right?
We use the video camera, but only for picture acquisition.
Training.
So we can use this video to help the people who are doing the attribution recognize the individual objects, because our algorithm is able to differentiate between people, laptops, and even coffee cups. Yes, and coffee cup in the 80 by 80 picture sometimes looks like I don't know, two hot pixels. The same is with the power adapter of the laptop, which is also generating some type of a heat. So for a person who is doing attribution, it was not possible to mark those objects correctly. That's why we have this video camera next to the IR camera, making videos at the same time. So it's just possible to do the proper attribution, and sometimes it was, even with the camera, it wasn't really possible to do this right. Yes, so let's say some percentage of the images we just need to discard.
Then I've got a couple of questions which are related to neural network architecture. So one is just what's the architecture, how big is it? And secondly, about quantization, do you use quantization, and what bit widths do you use if it's quantized?
Yeah, so maybe I will answer the second question because I know the answer. Of course, we are there is a quantization of the network because it minimize the network and minimize the computational complexity. I'm afraid that I can't answer the question exactly how this quantization was done, and I think that the network is a single shot detector. But David, you may correct me if I'm wrong.
The answer is correct. It's a generally available neural network with an SSD detector on top.
And then finally,
I can answer the question about quantization. Well, we use Greenwave's tools and libraries to quantize the network. So this is how we did it.
Okay. So we've answered that one and that one. And did you do any performance comparison between normal images and fisheye images?
I don't know if I understand the question correctly, but no, we didn't, because first of all, we decided that it probably doesn't make sense, and it's not that relevant for the neural network algorithm about if we are using the fisheye or trying to make this image like semi-flat. So we decided that maybe we can, if we are talking about the coordinates, we will be doing this computation in the cloud if necessary, but we haven't made an like direct comparison on the performance.
Okay. There's one other question I've got, which is, did you try mixed precision in the network, like mixing between int8 and FP16? Given that you used Greenwave's tools, I can probably answer that question, which is that GAP8 doesn't actually support FP16, so that wouldn't be possible on GAP8. GAP9 does, and also supports bfloat16 and would support mixing precision, but our experience generally on SSD networks is that mixed is not really necessary. You can do a very good job with 8 bits and less. There's no other questions at this point. Any other questions before?
I see that Evgeny actually would like to answer you see any performance comparison on normal images and fisheye corrected images? And I see that Evgeny would like to answer, but I don't know how to enable.
No, I don't know how to enable it either.
Okay.
No, it's gone away.
He's gone away.
I think it's there. So why not daily? I've got one other question. Why not daily calibration of sensors per day during the nights when there's no humans? So using the night as a dark surface to calibrate the sensor, the IR sensor.
We tried this. We tried this calibration, but the problem is that the calibration in practice should be done in the same conditions when the device is operating. And in many places, like in the office, for instance, the temperature during the night is different than during the day. So it's not something which will really help us a lot. But again, right now, we end up with the algorithm which, let's say, almost does not need anything beside the, let's say, initial calibration.
I've got one last question, given that there's none left, which I think is as a development project, and you've worked on developing other things during your professional career. This is a development project which integrates tinyML, which integrates embedded. How would you say this compares in terms of difficulty, in terms of challenges, in terms of, would you say it's a normal project? Would you say it's more difficult, less difficult?
Definitely it was the most difficult project I've made. Yes, definitely, because of many things. The first of all is its coordination of effort of many teams. Yes, as a hardware product, so you have hardware engineers, firmware engineers, you have the industrial engineers, mechanical engineers. You have a lot of people who need to attribute the data. You need also people who will generate this data, yes, because if you'd like to train the model with millions of pictures, yes, you need to collect those pictures, you need to process them. So it's a huge effort. It's a huge effort. The complexity of the device comparing to the previous devices we made is a different class, yes. So the key point here is to be able to coordinate work of many different teams. We were cooperating a lot with the Greenwaves team during the development, and it was a very good cooperation, which helped us a lot. And I think also another kind of a success factor is that we were able to launch mass production just after 1 year. We made the decision we will be doing this project. So it was 12 months, just 12 months from idea to the project. Of course, as I said before, it's kind of a continuous development. The model is getting better and better. Accuracy is continuously growing. We are still, coming up with new ideas how to improve. We are still acquiring a lot of different photos in different situations. So it's still live project, which is also something a bit different to what I was doing before, yes, when the product was a certain life cycle, and usually when you release to the customers, you were switching into kind of a maintenance mode. But here, this product is still being actively developed, and we still have ideas how to make it much better.
There's still actually there's now many more questions that have actually been added in. I don't know how long we can go on answering them for, but I think we've got time. I think we've got time for the moment. So how do you wait? I have first question, which was on network accuracy. So I think this is asking for actual accuracy of your network. I don't know whether that's something you're willing to give out, but
I'm afraid I can't answer this.
Yeah, okay. I would imagine you can't.
It's really good. No, it's really good. I mean, we can compare the accuracy of our product to the competition. Sometimes we are better. Yeah, I think it's honestly speaking, I would say it's performing much better than I initially thought it will be performing, given the resolution of the camera. Yes, I'm unable to distinguish people, but the algorithm often is able to do this much better than a person.
Yeah, it's seeing things that you aren't. How do you update your model on its existing deployments? That's an interesting question.
Yes, our infrastructure supports full OTA, so over-the-air firmware update. We can update firmware of the device remotely, completely. Yes, so we schedule this in the cloud. It will be transferred to the Beam device over our gateways, so we can do this fully remotely. I think that the whole firmware upgrade procedure takes something like 2-3 minutes. So of course it needs to be done carefully, not to interrupt with the normal operations of the device. But it's like a separate topic. Yes, it's more on the firmware management side. But in this situation, of course, there is a BLE connection between the gateway and the PortalBeam. During this connection, we are pushing the new update. It's processed on the device.
One question about have you ever considered adding a passive infrared sensor for kind of detecting that people are close to the?
That's actually a very good question. That's a really funny story behind this, because the initial design had actually here in this place a small DOM and PIR sensor, but at some point we looked at this and we decided, oh man, this is ugly. We don't want it.
Yeah. Another question about privacy, which is an interesting one, which is basically, yeah, okay, you know that it's an infrared camera and that you can't see, people in infrared camera. In fact, you also know that the radio is really slow and it's really unlikely you can take a high resolution photo of it. But how about your customers? Do they know? They just see a camera.
Yeah, that's actually a problem, yes, because the first approach was, okay, let's try to hide this camera, yes, because it would be the perfect solution. As you can see here, we have this black panel which is IR transparent, but it is transparent for IR LEDs, but it's not transparent for the heat, and we have the heat camera. So we were somehow forced to make this camera not covered. And yeah, there are concerns. But the good thing is that this camera is the appearance of this camera is like it's not camera, like it's some kind of a sensor. So it's not attracting so much people. But of course, we have a lot of communication and education to customers and to the people that. This is something you shouldn't be worried about. But yeah, sometimes it's still a kind of a concern for the customers.
So another question, which I think you probably won't answer, which is, have you filed any patent applications for this product? Which I think is well, I presume that you filed patent applications all over the place for it. But you're not going to tell what they are. But.
I can answer.
Yeah, I thought not. And then there's another question. Any uncertainty evaluation for the final trained network? If yes, how was the detection algo calibrated? I'm not sure I fully understand that, but.
I'm not sure as well, but of course we are. I mean, during the development, during the training. I mean, we are not doing anything super sophisticated. Just we are trying to adhere to the best practices So training with different data sets, trying to make sure that the data set is not, let's say, biased somehow. Yes, so we are training more against some use cases than others. It's a very much continuous process, and we have of course some kind of a data sets like exclusively selected for the verification, and usually we compare our improvements against those data sets, but there is probably something more I'm not aware.
Okay, that's completes the questions that we have here. So thank you very much, both of you, and thank you, Lucas, for answering all of those questions. We actually got through, I think, 23 of them, which we didn't answer all of them, but
thank you very much, Lucas. Again, A on devices, ARM, Deep Light, Edge Impulse, EMSA, PhotoHub, GreenWaves Technologies, Rovity Incorporated, HOTG, ImagiMob, iTemis, ClickAttack, Latent AI, Maxim Integrated, Analog Devices, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Rixen, SAP, Seed, tinyML, Sony Semiconductor Solutions Corporation, ST, Stream Analyze, SynSense, Syntian. ARM, AI Virtual Tech Talks. Please have a look at arm.com Tech Talks. Edge Impulse, the leading edge ML platform. Qualcomm AI Research. Syntian, end-to-end deep learning solutions for tinyML and Edge AI. Deep Light, ClickAttack, global IoT solutions. Reality AI, add advanced sensing to your product with Edge AI tinyML.
Renesas.
Broad and scalable edge computing portfolio, microcontrollers and microprocessors. So who is Renesas? Okay, I did notice. And strategic partners, PhotoHub, Maxim Integrated, Latent AI, Micro AI, NXP, and Seed. Going up, SenseML, ST, SynSense, and the silver strategic partners right in front of you. So let me finish today's talk. Perfect timing, actually. Thank you very much for coming today, Lucas, David. Let me remind to everybody that all the video will be uploaded to tinyML website. I will share as well on the GreenWaves linked platform. And thank you all very much and have a great day.